Let's talk about caching. It's this invisible engine that makes the modern internet feel so incredibly fast. It is literally the secret sauce behind why your favorite apps and websites load in the blink of an eye. So today, we're going to pull back the curtain and see exactly how it works. So let me ask you a question you've probably never even stopped to think about. Why is your Instagram feed so fast? You know the feeling, right? You pull down to refresh and bam, a whole new set of photos just appears. It feels instantaneous, almost like magic. But it's not magic. So how is that even possible? Well, that feeling of instant is absolutely not an accident. It's actually the result of solving a huge, fundamental engineering challenge. And that challenge has a name: latency. You've felt this before, we all have. It's that tiny, sometimes infuriating delay between when you click something and when the thing actually happens. That's latency. And in the world of software, engineers are obsessed, and I mean obsessed, with shaving off every single millisecond. Because those milliseconds are the difference between a user who loves your app and one who's about to delete it. Okay, let's actually follow the data on its journey. When you refresh your feed, your phone sends a request out to a server somewhere. Let's say that takes about 100 milliseconds. Then that server has to turn around and ask the database, hey, can I get the latest photos? That's another 10 milliseconds. The database finds the info and sends it back to the server. That's 10 more milliseconds. And finally, the server bundles it all up and sends it all the way back to your phone, another 100 millisecond trip. So you add all of that up and the entire round trip takes 220 milliseconds. Now you might be thinking, that's less than a quarter of a second. Who cares? But online, that's a huge amount of time. It's the difference between an app that feels snappy and one that feels sluggish and slow. This right here, this is the exact problem that caching was invented to solve. The biggest delays, as you saw, come from those long trips to get the data. So what if you didn't have to make that trip every single time? And that brings us to the hero of our story: caching. At its core, caching is a really beautiful and simple idea. It's all about reducing repeatable work. Instead of doing some heavy lifting like fetching information from a faraway database over and over and over again, you just do it once, you save the results somewhere really close, and then you just grab that handy copy the next time you need it. It's that simple. And just look at the kind of impact we're talking about. Remember that 10 millisecond query from the server to the database? Well, if that data is stored in a nearby cache instead, that same query takes just 1 millisecond. That is a 10 times improvement. It's a total game changer. And this leads us to this key concept of a cache hit. A hit is when the data you're looking for is already in the cache, waiting for you. And the goal is to get that hit rate as high as possible. So if we can get a 90% hit rate, that means 9 out of 10 times we get that lightning fast 1 millisecond response. We only have to make that slow, painful trip all the way to the database 1 time out of 10. The average speed just skyrockets. Okay, so this all sounds perfect, right? It's like a magic bullet for speed, but of course, it's not that simple. Nothing in engineering ever is. Once you decide to use a cache, you're immediately forced to answer two very, very difficult questions. And this is the fundamental trade-off right here. You gain an incredible amount of speed, but you pay for it with a whole new world of complexity that you now have to manage. If you get it right, your system flies. But if you get it wrong, things can get so much worse than when you started. So here's problem number one. The cache is just a copy of the data. The database, that's the real source of truth. So what happens when the data in the database changes? How do you make sure the copy sitting in your cache doesn't get old, stale, and just plain wrong? And right on the heels of that is problem number two. Your cache has a very limited amount of memory. Think of it like a small, expensive shelf. Your database, on the other hand, is like a massive warehouse. So when your little shelf is full and some new, popular item needs a spot, you have to kick something else off. But what do you get rid of? How do you decide? When you answer those two questions poorly, well, that's when you enter the dark side of caching. Because if your strategy is off, you can end up creating brand new problems that are way worse than the latency you were trying to fix in the first place. Yeah, it sounds totally paradoxical, but it is absolutely true. If your cache almost never has the data that users are asking for, what we call a poor hit rate, then every single request adds a wasteful, pointless extra step. You first check the cache, find nothing, and then you go to the database anyway. You've just added extra work and made your system slower. This slide shows a classic nightmare called cache trashing. Just imagine your cache can only hold 3 items. A user asks for item 1, then 2, then 3. The cache is now full. Then they ask for item 4. To make room, the cache kicks out item 1. But what if the user's very next request is for item 1 again? Well, it's gone. That's a cache miss. You have to go all the way back to the database. You're stuck in this horrible loop of kicking data out just moments before you need it again. The other huge problem is stale data. And this is where we run into a concept with a fancy name, eventual consistency. But really, all it means is that for a little while, the copy of the data in your fast cache might be slightly out of sync with the real data in the database. They won't match perfectly. And this is where the context of your application is everything. Is it okay for the like count on a YouTube video to be a few seconds out of date? Yeah, probably. The consequence is basically 0. But what about your bank account balance? Absolutely not. You cannot have stale data when it comes to financial transactions. The consequences there could be catastrophic. All right, so we get the what and the why of caching. But where does this thing actually live inside a system's architecture? Well, there are 3 really common places. You can have a cache running right in memory on the same machine as your application. A lot of databases also have their own caching systems built right in. But for really big, large-scale systems, you'll almost always see a separate dedicated service called a distributed cache. But, for a massive system, think Netflix or Amazon, the real answer is often all of the above. They use multiple layers of caching, each one with a very specific job. That said, the one that software engineers tend to interact with and design around the most is that big, shared, distributed cache. So, after all of that, what's the big picture? What's the one thing you should really walk away with about caching? This quote from our source material just says it all perfectly. Caching is an unbelievably powerful tool. It saves time, it makes apps feel amazing. But it is not a simple fix. Your caching policy, the rules for how you update data and what you kick out, and the placement of that cache, those choices are absolutely critical. You have to think deeply and make the right choices for your specific system. At the end of the day, caching is a game of trade-offs. It's a constant balancing act between speed, cost, and complexity. The real question isn't if you should cache, but how you should do it. So I'll just leave you with this to chew on. For your next project, what's your caching policy going to be?